Hey everyone, welcome to today's Explainer. Consider me your lead engineer for this session. Our goal today is absolutely crucial. We're going to take your AI application from a fragile, kind of temporary script and build it into a rock-solid, production-ready system. If you've been messing around with large language models, you've probably hit that wall, right? Where the app just completely stops being smart? Well, today we're fixing that by architecting persistent AI memory. Let's get right into it.
I really want you to ask yourself this question right now. Why is your AI forgetting literally everything when the server restarts? You spend all this time chatting, giving it all this context, teaching it exactly what your preferences are, and then, poof, you restart the app, and boom, total amnesia. It's incredibly frustrating for you as a developer, but imagine releasing that to actual users? Yeah, no way. It's a complete deal breaker for a real production environment.
Okay, let's do a quick code review. We've got our self.short as an empty list and self.long as an empty list. When we all start out, we write something exactly like this. We just append user messages to a basic Python list and chuck it back to the model. But I gotta be honest with you. In a production environment, this is a classic junior developer trap. It kind of feels like memory, but it's really just an illusion.
Let's systematically break down why this naive design is basically guaranteed to crash your application. First up, all of this exists only in RAM. The second your app restarts, that memory is completely wiped, gone. Second, you've got infinite growth. If you just keep appending messages to a list, eventually it's going to consume a huge amount of memory and slow your retrieval down to an absolute crawl. Third, and honestly this is the most dangerous one, you will eventually hit token overflow and just crash the LLM entirely. And finally, there's zero database or persistence layer backing any of this up. It's just not a sustainable way to build.
So, here is our sprint plan to fix it. We have a clear refactoring roadmap. 1. The persistent SQL layer. 2. Mastering token management. 3. The modern memory pipeline. 4. Knowledge compression techniques. And 5. The intelligent platform. Okay, let's dive into this refactoring roadmap.
Section 1. The persistent SQL layer. It is time to jump into our first major code upgrade, moving from that temporary RAM over to a structured, persistent database.
By simply importing SQLite 3 and creating a knowledge storage class that connects to a memory.db file, we are laying down the actual concrete for our persistent infrastructure layer. Without this knowledge storage, your AI literally cannot keep context across sessions. This single connection right here, it transforms your app from a goldfish into an elephant. We are finally storing data on a disk, not just in volatile memory.
And this builds right into a beautifully simple, effective workflow. Step 1, we store a specific preference like user prefers Python. Step 2, we retrieve it. Step 3, we get our expected output. It's simple, sure, but it fundamentally changes the game for us. We can now safely store user preferences, historical reasoning, agent states, the whole shebang, and actually pull them back up weeks or even months later. True continuity is suddenly possible.
Section 2. Mastering token management. Because now that we can store everything permanently, well, we've kind of introduced a dangerous new problem. We have to prevent overflow.
The difference between these approaches is brilliant. A basic buffer just counts messages, right? Maybe you keep the last 5. But message sizes vary wildly. One's a quick sentence, the next is a massive paragraph. That gives you really poor token control and incredibly weak overflow prevention. But a token-based system, that tracks the actual token count. This gives you high precision, excellent scalability, and most importantly, really strong overflow prevention.
You absolutely have to ground this technical issue in business reality. If you ignore context limits, you aren't just getting an annoying error message. You are literally paying for it. Sending massive, unmanaged conversation histories to an LLM drastically increases your inference costs. It creates high latency, meaning your users are just sitting there waiting. And because the model gets overwhelmed, it leads to context truncation, massive model confusion, and ultimately just terrible answer quality.
So here is the production-level fix. We build a token memory module. The real magic here is this while loop. While total tokens are greater than our max limit, remove the oldest. We're dynamically calculating exactly how many tokens our context is eating up. If it breaches our safe limit, say 2,000 tokens, we just loop and strip out the oldest context until we're back in the safe zone. This sliding window guarantees we never overflow our context window. The result? Smaller prompts, way faster inference, and much lower operational costs.
Section 3. The modern memory pipeline.
This is where we combine our SQL storage and that token trimmer into a complete advanced architecture.
This is the exact flow of data in a modern, production-grade system. It starts with a conversation buffer for that immediate, recent context. Then, that buffer passes right through our token trimmer, so we don't break the model. But remember, we also have our long-term database storing persistent facts now. Step 4 is where the real magic happens, the hybrid retriever. When a user asks a question, we don't just blindly look at the short-term chat. We pull the recent context, we query our SQL database for the hard facts, and we do a semantic vector search. We combine all of this into one perfect, highly relevant prompt for the LLM.
Section 4. Knowledge Compression Techniques. Let's talk about how to optimize our long-term storage so it doesn't just turn into a bloated mess over time.
Think about it. If your user has been chatting with your app for a solid year, you absolutely cannot keep all that data raw in your active retrieval flow. Sending an entire 500-message history is insanely expensive and totally confusing for the model. Instead, we use knowledge compression. Periodically, we just have the AI summarize the core facts. We distill those 500 messy messages down to one crisp, clear database entry. User prefers breakout trading and nifty options. Boom. We separate short-term memory from long-term memory, and we heavily compress the past.
Section 5. The Intelligent Platform. We've built the database, managed the tokens, wired up the pipeline, and compressed the data. Let's zoom out.
Now, what's really fascinating about this architecture is the cognitive analogy. We are basically mirroring human architecture in our code. Human working memory, that's our conversation buffer, holding what's happening right this second. Our human long-term memory is that SQL database we just built. The active human recall is our hybrid retriever pulling the exact right facts. And human semantic association, how we intuitively connect related ideas, that's the vector database. You aren't just writing basic scripts anymore. You are quite literally architecting an artificial cognitive system.
Let's summarize everything we've covered in this explainer with a core insight straight from our design documents. Knowledge storage is the persistent database layer that enables AI memory and long-term intelligence. We've taken a fragile, temporary chat script that forgets everything, and we've completely transformed it into a persistent, intelligent platform that can actually remember, retrieve, adapt, and personalize over time.
We've made a massive leap in our code today. You've got the blueprints now. The SQL foundations, the token sliding windows, the hybrid retrieval pipelines, and those crucial knowledge compression strategies. The only thing left for you to do is fire up your IDE and get to work. So armed with this new architecture, how will you build your next intelligent platform? Thanks so much for joining me for this explainer, and hey, happy coding!